Farmer again. Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. So let P be a proof system for Church's type theory. So this will be a system given by a set of axioms and rules of inference. So we're going to make some fairly obvious definitions about P. We're going to say that P is sound if whenever A can be proved from H in P, that implies that A is a semantic consequence of H in the general sense. And we're going to say that P is complete in the general sense if whenever A is a semantic consequence of H in the general sense, that implies that we can prove A from H in P. And P is complete in the standard sense. That means whenever A is a semantic consequence of H in the standard sense, then we can prove A from H in P. Now, a very important theorem is that there is no proof system for Church's type theory that is sound and complete in the standard sense. So I'm going to prove that now. So let PA here be the theory of Church's type theory that formalizes second-order Peano arithmetic. So it has the three axioms of Peano arithmetic. The axioms that say that 0 is not the successor of anything, the successor function is injective, and we have the induction schema. Now, this theory has a single standard model up to isomorphism. That means all the models of this theory are isomorphic. They're essentially the same. Now suppose that P is a proof system for Church's type theory that is sound and complete in the standard sense. So then by the completeness, or I should say the soundness of P, and Gödel's incompleteness theorem, there is going to be a formula A such that A, or I should say a sentence A, that would be a closed formula A, such that A is true in this model, and we cannot prove A from the axioms of PA in our proof system P. Now, since P is complete in the standard sense, 2 implies this. So not having a proof means we don't have a semantic consequence. And that means that we have not M is true, A is true in M. That's because what this says here is that for every standard model of gamma, A is true in that model. But there is only one, I should say, it's not the case that for every standard model of gamma, A is true in that model. But there's only one such model. That means A cannot be true in M, and this contradicts 1. So this result contradicts this result. Hence, there is no such proof system P. Okay, so that says, just repeat, that says there's no proof system for Church's type theory that is sound and complete in the standard sense. But there is a proof system for Church's type theory that is sound and complete in the general sense. And this was given by Henkin in 1950. This was essentially his PhD thesis. And this is what I would call the arch theorem of Church's type theory. It's the most important theory of Church's type theory. And it's the reason why our semantics is based on general models instead of standard models. Or I should say our main semantics. Now, as a corollary of this, we can see that Church's type theory is compact with respect to general models. That means if a theory is finitely satisfiable, it is satisfiable. Now, another important theorem is Andrews in 1963. He came up with a very simple proof system for Henkin's version of Church's type theory that is sound and complete in the general sense. And so Henkin's version of Church's type theory is very simple. This is essentially what we've given. It's the backbone of Alonzo. And Andrew's system is very simple. So what I'm going to do now is give a proof system for Alonzo, and it's going to be based on Andrew's system. And the first 4 kinds of axioms are very similar to the axioms in Andrew's system. And I'm not going to go in detail what these say. I'm just going to give an overview of what they mean. The first says that there are only 2 truth values that are represented by T and F. There's only 2 such truth values. The second says that 2 values are equal. If 2 values are equal, then they satisfy all the same properties. The third says that 2 functions are equal if and only if, when we apply these functions to an argument, we always get the same value. And the fourth is beta reduction. Beta reduction says we can do beta reduction in the normal way, provided that the argument is defined and the result may be that this and this are both undefined. So that's why we use quasi-equal here. And of course this is provided A is free for the variable in B. So these 4 correspond to Andrew's original system, and they're really the axioms we need for core Alonzo. So we need some, or I should say, these are the axioms we need for core Alonzo without dealing with undefinedness, but we also have axioms for dealing with undefinedness. And these are pretty simple. If you go to the definition of a general model, we can pretty much read off of these definitions. So the first says variables are always defined, constants are always defined, equalities are always defined. If either component of an equality is undefined, the equality is false. It says that predicate applications are always defined. And if either the function or the argument of a predicate application is undefined, then the predicate application is false. Otherwise, if we have a function application, if either the function or its argument is undefined, then the function application is undefined. Function abstractions are always defined. And then we have this technical level. We need this to show that quasi-equivalence and equality are the same when A and B are defined here. This is missing. When A and B are defined. Okay, so those axioms we need for core Alonzo. For full Alonzo, we need some additional axioms. We need two axioms for definite description. So if X is a unique value that satisfies A, then the X that satisfies A will be a member of the values that satisfy A. In fact, it's a unique member. If there is not a unique X that satisfies A, then the definite description is undefined. Now for tuples, what we need is that the first says that our pairing operation is always defined. The second says that for all members of alpha cross beta, all members of alpha cross beta will be a pair, will be something we can get by forming a pair. And the third says the pairing operation is injective. if you think a moment of what these really are saying, this is saying that we have total, this is saying we have surjective, and this is saying we have injective. So these axioms say that there's a bijection between this and the things that we can form as pairs. Now the axioms for a list are very similar to the axioms we have for the natural numbers. The list construction operation is always defined. Nil is never equal to a list construction. The list construction operation is injective, and this is the induction principle for lists. And now we have just two rules of inference, modus ponens, which we've seen before, and quasi-equality substitution. So here, if we have a quasi-equality and another formula, we can replace in that formula one occurrence of A by an occurrence of B. We can do that because they are quasi-equal. And there's a proviso here: the occurrence of A in C cannot be the first argument of a function, abstraction, or definite description. So in other words, it can't be this, we can't replace this. And similarly, we can't replace this. Okay, so I'm going to give a conclusion now to this topic, our topic of simple type theory. I'm going to first say that simple type theory is a logic that is effective for practice as well as theory. And this is unlike first-order logic. First-order logic is essentially a logic for theoretical purposes, not practical purposes. So simple type theory is more expressive and more convenient than first-order logic. It is much closer to mathematical practice, much closer to how people do things in practice. It's based on the same principles as first-order logic. It includes the full machinery of first-order logic. So anything you can do in first-order logic, you can do in simple type theory. And it integrates predicate logic that we have from first-order logic, as well as function theory and type theory. So this is why it's an important underlying logic for functional programming. And it illuminates the model theory of first-order logic. Trying to understand the model theory of first-order logic can be increased, your understanding can be increased by looking at the model theory of simple type theory. And finally, simple type theory is a basis for several of the most popular proof systems in existence today. Now, Alonzo is a version of Church's type theory that's designed for practical use. And one thing it does, unlike most logics, it admits undefined expressions. Core Alonzo has a very simple syntax and semantics. Full Alonzo, however, has a more complex syntax and semantics, but it's well suited for reasoning about structures. Now, in my paper, 7 Virtues of Simple Type Theory, I listed 7 virtues of simple type theory. I'm going to take this opportunity to read them off. Simple type theory has a simple and highly uniform syntax. The semantics of simple type theory is based on a small collection of well-established ideas. Simple type theory is a highly expressive logic. Simple type theory admits categorical theories of infinite structures, like the structure of the natural numbers or the real numbers. And there is a proof system for simple type theory that is simple, elegant, and powerful. This is basically Andrew's system. Henkin's general model semantics enables the techniques of first-order model theory to be applied to simple type theory and illuminates the distinction between standard and non-standard models. This refers to the fact that simple type theory illuminates the model theory of first-order logic. And finally, there are practical variants of simple type theory that can be effectively implemented. Now, here are a list of references that I will quickly mention. There's Bertrand Russell's original paper where he introduces the theory of types, the ideas that started type theory today. There's Whitehead and Russell's Principia Mathematica, which is using the theory of types to formalize, really for the first time, a major chunk of mathematics. There's Church's presentation of simple type theory, in which he uses lambda notation, and this is what is now called Church's type theory, and this is the beginning of, this is really the beginning of theory of types being used in computing. And there's Henkin's completeness in the theory of types. This is when Henkin shows that there is a sound and complete, in the general sense, system, proof system for Church's type theory. And then there's this paper where Henkin shows that you can present Church's type theory very simply using just the ideas of equality, function application, and function abstraction. And in this paper, Peter Andrews takes that simplified system of Henkin and comes up with a very simple proof system for it. Then there is an excellent book by Peter Andrews on logic that has a completely covers Church's type theory. And then there's my paper on the 7 virtues of simple type theory. And finally, I want to mention the book that you know about that I'm working on, Simple Type Theory, A Practical Logic for Mathematics, Computing, Engineering, and Science. Okay, so this completes the last lecture of the last topic for this course. Thank you for your attention.